Chapter 22 Nuclear Propulsion and Remote Power. In this chapter, we are going to study the reactor for naval propulsion and also the radioisotopic power for deep space exploration. Nuclear processes are logical choices for compact energy sources in vehicles that must travel long distance without refueling. The most successful application is in the propulsion of naval vessels, especially submarines and aircraft carriers. Besides employing reactors for large-scale electric power generation, radioisotopes can be utilized to supply smaller power and basic thermal heating. Thermoelectric generators that use the isotope plutonium-238 provide reliable electrical power for interplanetary spacecraft. The discovery of fission stimulated interest on the part of the U.S. Navy in the possible use of nuclear power for submarine propulsion. The principle of virtue of a nuclear-powered submarine is its ability to travel long distance at high speed without refueling. It can remain submerged because the reactor power plant does not require oxygen. USS Nautilus was the world's first operational nuclear-powered submarine. The power plant for the Nautilus was a water-moderated, highly enriched uranium core with zirconium-clad plates. The submarine's first sea trials were made in 1955. Some of its feats were a 1,400-mile trip with an average speed of 20 knots, the first underwater crossing of the Arctic ice cap, and traveling a distance of more than 62,000 miles on its first core loading. Subsequently, the USS Triton, which demonstrated a twin reactor propulsion system, reproduced Magellan's trip around the world, but completely submerged. This figure shows the Nautilus, decommissioned in 1980, now displayed in a museum at Groton, Connecticut. The U.S. nuclear fleet was built up during the years of the Cold War, with more than 100 nuclear-powered submarines, a number of aircraft carriers, and a few cruisers. The first of the aircraft carriers was the USS Enterprise, deployed in 1961 and deactivated in 2012. It had 8 reactors, 2 for each of its 4 propeller shafts, 85 aircrafts, and 58 30-men. This figure shows the carrier with the Einstein's familiar formula, spelled out on the deck by members of the crew. The accompanying ships are the cruiser USS Long Beach in the center and the frigate USS Bainbridge on the top, powered by 2 reactors each. So all the 3 ships are powered by the nuclear power. Since then, more than 10 additional carriers have been built, but with only 2 reactors per ship. This figure shows a generic naval propulsion system configuration. The pressurized water reactor are the most common reactors used in the ships and submarine. As shown in this figure, you have the reactor core producing the heat, and the hot water will flow through this steam generator. Inside this steam generator, the water from the secondary loop is being boiled, then the steam is produced, and the steam will rotate the turbine. Then in this figure, the turbine is connected to the propeller through this gearbox directly. The steam will also rotate an electric generator to produce the electrical power needed by the submarine or by this ship. So the nuclear steam will supply system of a vessel. It can be configured in multiple ways. As depicted in this figure, the steam is connected to this propeller directly through the gearing connected to the turbine. Alternatively, the turbine generator supplied electric power can be fed to a motor that turns the propeller to battery storage and to equipment such as pump. And it means that there may be another configuration. So the steam is used to produce electricity. Then the electricity will power the electrical motor to rotate the propeller, which is the most modern design of the nuclear powered submarine system. Now we have an example 22.1. So the Nautilus has a shaft power of 13,400 horsepower. Assuming the submarine averaged speed of 17 knots, we'd like to calculate the fuel consumption for its first core loading. From the previous explanation, we know that the first core loading produced 62,000 miles. Okay. First, we calculate the total operation period, so total duration of length of the operation. And we simply use the total distance traveled divided by the average speed, so we get the duration of time. The total distance is 62,000 miles. Then the velocity is 17 knots. Then we convert the 17 knots to miles. Okay, so 1 knot is equal to 1.15 mile. Then we get 3170 hours. Then we assume the thermal efficiency was 22%. Means that you produce 100 joule of heat, then 22% is converted to the mechanical power. Then the uranium-235 fuel consumption over this 132 days, so 3170 hours is equivalent to 132 days, can be calculated by this formula. So the mass of the fuel consumption is equal to the megawatt a day, that is total heat produced, times this coefficient, 1.3 gram per megawatt a day. Means that to produce 1 megawatt a day of thermal heat, you will consume 1.3 gram of the fuel. Okay, so we use the shaft power divide the efficiency, so that is your thermal power. Okay, thermal power. So we use 13,400 horsepower. Then we convert it to watt. So 1 horsepower is equal to almost 750 watt divided by 22%. Then times 132 days. Okay, times 132 days. Then times this coefficient. Then we divide 1 million to convert the watt to megawatt, so that we can get a total fuel consumption, that is 7.8 kilogram. The nuclear-powered vessels are mainly military submarines and aircraft carriers. At the present day, Russia is the only country that currently has nuclear-powered civilian surface ships. Most of them are icebreakers, but one is a container ship. This figure shows the nuclear icebreaker produced by Russia called Yamo. And the bottom figure shows that the icebreaker is traveling to the North Pole, carrying the tourists. So since 1989, the nuclear-powered icebreakers has also been used for tourist purpose, carrying the passengers to the North Pole, as shown in these figures. Each participant will pay up to US $25,000 for a cruise lasting 3 weeks. The nuclear propulsion mainly have 3 advantages. First, Nuclear power does not use oxygen, so the submarine can stay submerged for almost unlimited time, while a diesel-powered submarine can only stay submerged for a few weeks. Second, nuclear-powered submarine warships can run almost continuously without fuel supply because the nuclear power is very efficient. You do not need to refuel the reactor very often. Third, the nuclear propulsion system is very efficient. It is a very compact system. There is no need to carry the fuel. When compared to its conventional counterpart, a nuclear aircraft carrier can carry twice the amount of aircraft fuel, 30% more weapons, and 300,000 cubic feet of additional space, which would be taken up by air intakes and exhaust trunks in gas turbine-powered carriers. The Operation Sandblast was the code name for the first submerged circumnavigation of the world, executed by the United States Navy nuclear-powered Radioactive submarine USS Triton in 1960. So this trip took over 60 days, and it can only be achieved by a nuclear-powered submarine, remain submerged for more than 2 months. This figure shows the potential choice of your power source for different scenarios. For higher power, on the top of this figure, the best choice will be the fission reactor, no matter you need it for short period of time or longer period of time. And for longer period of time, the fission reactor and other types of energy production method can be chosen. If you need lower electrical power for short period of time, you may choose the chemical power. So for long duration missions requiring kilowatt of electrical power, the nuclear reactors are the energy source of choice, while for lower power requirement, photovoltaic and radioisotopic source are in competition. However, deep space probes cannot exploit solar energy due to the faintness of sunlight. Reactor and radioisotopes both produce heat, but if electricity is the desired energy form, then a means to convert thermal energy to electric energy must be employed. Terrestrial reactors utilize dynamic heat energies such as Rankine for steam and Brayton for gas power cycle, which are also options for space reactors. For a normal nuclear reactor, it will use the Rankine cycle or the Brayton cycle to convert the heat to electricity. Alternatively, static power conversion methods such as thermoelectrics and thermionics may be used, which can convert the heat to electricity directly. Commercial beta-voltaic batteries using tritium are available for use in terrestrial applications. For instance, nano-tritium batteries, as shown in this figure, can produce a small current, 100 nanoampere. This small current can continuously charge a secondary battery. Here we have a simple example. If the conversion efficiency of a 1 microwatt beta voltaic unit employing tritium is 3%, compute the electrical power output of the unit when it is 10 years old. This battery employs the radioactive decay of tritium, which will produce, then it uses that to produce the electricity. And the electrical power will be proportional to the activity, and the activity will follow this exponential decay rule. And from the previous study, we have this radioactive decay equation. And because the P power, electrical power, is proportional to the activity, so we can simply replace the A by the P in this equation. So the electrical power P at a certain time t is equal to the P naught, then times 1 over 2 to T over Th. Here the T, lowercase t, is the duration of time, and the Th is the half time of tritium, which is a constant. Then, next step, we replace the P naught by the initial power, that is 1 microwatt. Then the duration of time is 10 years, and the half-life is 12.3 years, which is found from the reference. Then the result is 0.57 microwatt. It means that after 10 years, this battery can still produce 0.57 megawatt of electric power. This figure lists several radionuclide that may be suitable as standalone power sources. Selection criteria include the half-life, which need to be appropriate to the mission duration. The specific power of a radioisotope may be calculated from this formula. Sp, the specific power, is equal to Sa, specific activity, times the Ed, that is the energy released per decay. So the Sa is the specific activity, that is the number of decay per second per unit mass, then times the Ed, that is the energy release per decay. So you get the energy per second per unit mass, which is power per unit mass. That is essentially your specific power. In example 22.4, we are going to calculate the specific power of cobalt-60. From the table in the textbook, we know that the cobalt-60 release beta ray, whose maximum energy is 0.318 MeV, and also two gamma rays of total energy 2.5 MeV. With an average beta energy of approximately 1/3 of the maximum, the energy per decay is calculated in this way. So the Ed, that is the energy release per decay, is equal to the average beta energy, that is the maximum beta energy 0.318 divided by 3. Okay. As a rule of thumb, so the average beta energy is 1/3 of the maximum beta energy, plus the total of two gamma ray energy, which is given as 2.505 MeV. So we get 2.611 MeV. It means that for each decay, on average, the cobalt-60 is going to produce 2.6 MeV, this amount of energy. Then we use the previously calculated specific activity for the cobalt-60. We can calculate the specific power. So the specific power is equal to specific activity, then times the Ed, times the energy released per decay. So the specific activity for cobalt-60 is 4.19 times 10 to 13 BQ per gram. It means that for 1 gram of the cobalt-60 in 1 second, there are 4.2 times 10 to 13 decays. Then times this Ed, that is 2.611 MeV per decay. Then we get the MeV per second per gram. Then we convert the MeV to joule, so we get this value, that is power per gram. You need to note that this is the maximum theoretical thermal power you can acquire from this source. Depending on the energy conversion method, not all this energy may be recoverable. For example, the gamma ray has very high penetration ability, so it may leave your device and the gamma energy may not be recoverable. For long missions, such as interplanetary exploration, in which it is necessary to supply electrical power to control and communication equipment for years, nuclear power is needed because the sunlight may not be enough. The radioisotope thermoelectric generator, RTG, has been developed and used successfully for many missions. It uses a long-lived radionuclide to supply heat that is converted into electricity. This power source has many desirable features. The most important include long service life and continuous power production. And also it is independent from the sun, permitting visit to distant planets. The basic configuration of the RTG is shown in this figure. You have the heat source at the center, which is the heat is produced from the radioactive decay. Then you have the heat rejection fins and also the thermoelectric couples. The thermoelectric couples require the heat source and also the heat sink. By connecting the heat source, that is the radioisotope fuel, and also the heat sink, that is the cold environment in the space, it can produce the electricity. Typical of the RTGs is the one sent to the moon in the Apollo 12 mission. In this example, we are going to calculate the thermal efficiency for these thermoelectric couples. From this figure, we know that the thermal power of this radioisotope fuel is 1480 watt. Then the electrical power is only 74 watt. So by definition of the thermal efficiency, we simply use the electrical power 74 watt divided by 1480 watt. So we get only 5%. So compared to the Rankine cycle, the nuclear power plant, which is 1/3, the thermoelectric couples has very low thermal efficiency. Chapter 23, Radioactive Waste Disposal. Materials that contain radioactive atoms and that are deemed to be of no value are classed as radioactive waste. They may be natural substances such as uranium ore residuals with isotopes of radium and radon, products of neutron capture with isotopes such as those of cobalt and plutonium, or fission products with a great variety of radionuclide. Radioactive waste are produced throughout the nuclear fuel cycle, as shown in this figure. This diagram is the flowchart of the process that starts with the mining and ends with the disposal of waste. So uranium start from uranium mine and then go to the mill and produce uranium 308. Then enrichment process produce the fuel, then burn in the nuclear reactor. Then the spent fuel can be sent for permanent disposal directly or reprocessed to extract the useful content from the spent fuel, then continue this cycle. Therefore, there are two alternative modes shown in this figure. One is called the once through, which is used by the United States. So the fuel is used only once. After it is burned inside the reactor, it is sent for permanent disposal. Another one is called recycle. So the used fuel, the spent fuel, is reprocessed to extract the useful content, like the remaining uranium and the plutonium. The solid line represents the once-through fuel cycle, and the dashed line represents the recycle cycle. Sometimes these two modes are also referred as open and closed cycle, respectively. The sources of nuclear waste may include the following four categories. First is the meal tail. Uranium ore contains very little of the element uranium, approximately 0.1% by weight. The ore is treated at the processing plant known as mills, where mechanical and chemical treatment yields yellow cake, which is mainly U3O8, and a large residual called meal tailing. They contain mild radiation from the uranium decay chain. Tailings are disposed of in large piles near the mills, with an earth cover to reduce the rate of release of the noble radon gas, and that prevent excessive air contamination. The second source is depleted uranium. The separation process generates large amount of depleted uranium, known as tails. Depleted uranium is stored and could be used as fertile material for future breeder reactors. The third one is operation of reactors. This one is not shown in this figure. The operation of reactors gives rise to liquids and solids that contain radioactive materials from two sources. One is activation of metals by neutrons, producing isotopes of iron, cobalt, and nickel. The other is fission products that escape from the fuel tubes or are produced from uranium residue on their surfaces. The last one is spent fuel. After the fuel is born in the nuclear reactor, it became spent fuel. So the spent fuel resulting from neutron irradiation in the reactor contains the highly radioactive fission products and various plutonium isotopes, along with the sizable residue of uranium that is near natural concentration. According to current U.S. practice, the used fuel will be stored, packaged, and disposed by burial. In some other country other than the United States, the spent fuel from commercial reactors is being reprocessed. As shown by the dashed line in this figure, the recovered uranium is returned to the isotope separation facility for re-enrichment, and the plutonium is combined with slightly enriched or depleted uranium fuel to produce the mixed oxide MOX fuel, which is a mixture of UO2 and POO2. Only the fission products are subject to disposal. In this example, we are going to produce 100 kilograms of uranium from an ore whose grade G is 6%. And this uranium ore contains uranium-3 or oxygen 8. Okay. So we'd like to calculate the mass needed of this ore in order to produce 100 kilogram uranium. But pay attention that this ore contains the uranium in the form of U3O8, and the weight percentage is 6%. So the mass of ore is equal to the mass of U3O8 divided by the 6% G. Then the next question is, what is the mass of U3O8 that can give you 100 kilogram? Okay, so we know the mass of uranium is 100 kilogram. Then we use 100 kilogram to divide 3 times the mass of uranium. It will give us the number of moles of the U3O8. Then we multiply the molecular mass of this U3O8. And so we have this formula. And then we replace all the variable by its numerical value. So the mass of uranium is 100 kilogram, and the G is 6%, which is 0.06. And the mass of uranium, we use the uranium-238 mass to approximate, because more than 99% of the uranium in the nature is uranium-238. So simply that's 238, then times 3. Then the mass of the U3O8 is 3 times 238 plus 8 times the oxygen mass, 16. Then we can get 1965 kilogram. Then the corresponding mass of meal tailing can be calculated by this formula. So the mass of the tail is equal to the mass of ore minus the mass of U3O8, or it is equal to the mass of the ore times 1 minus G. Okay, so you have the mass of the ore that is calculated as 1965 kilogram. And because 6% will be useful, we're going to take it out. Then the other 94% will be the tail, which is 1847 kilogram. Next section is the waste classification. The first method to classify this waste is by defense and non-defense. So the defense waste are generated by reactor operation over the years for the stockpile of plutonium and tritium for nuclear weapons. And the spent fuel from submarine reactors was reprocessed. Okay. Basically, the defense waste is the waste from the military. On the other hand, the non-defense waste include those produced in the commercial nuclear fuel cycle, like the commercial reactor. Industrial waste comes from manufacturers who use isotopes and from pharmaceutical companies. Institutions include universities, hospitals, and research laboratories. It means that for the non-defense waste, it comes from civilian use of nuclear material. The second method of classification is by the type of material and the level of radioactivity. Therefore, we can have the high-level waste and also the low-level waste. The high-level waste are from the reactor operation. For example, there are fission products that have been separated from other materials in spent fuel by reprocessing. If we reprocess the spent fuel, we can extract this highly radioactive fission product. They are considered as the high-level waste. The second category is spent fuel, because such used fuel in the United States is to be disposed of in a high-level waste repository, so it is often thought as a high-level waste. So it means that even without reprocessing, this spent fuel is still considered as high-level waste. A third category is transuranic waste, called TRU, which are waste that contain plutonium and heavier artificial isotopes. The main source of the transuranic is nuclear weapon fabrication plants. The low-level waste is defined as material that does not fall into any other class. So if it is not a high-level waste, we can call it a low-level waste. The low-level waste has a small amount of radioactivity in a large volume of inert material and is generally subject to placement in a near-surface disposal site. The management of spent fuel at a reactor involves a great deal of care in mechanical handling to avoid physical damage to the assemblies and to minimize exposure of personnel to radiation. At the end of a typical operation period of 18 to 24 months for a pressurized water reactor, the head of the reactor vessel is removed and set aside. The whole space above the vessel is filled with borate water to allow fuel assembly to be removed while immersed. By use of movable hoist, the individual assembly weighing approximately 600 kg are extracted from the core and transferred to a water-filled storage pool in an adjacent building. This figure shows the arrangement of fuel assembly racks in the bottom of the spent fuel storage pool. Approximately a third of the core is removed. The fuel remaining in the core is rearranged to achieve the desired power distribution in the next cycle, and the fresh fuel assemblies are inserted into the vacant space. The water in the 40 feet deep storage pool serves as the shielding and cooling medium to remove the fission product residual heat. To ensure the integrity of the fuel, the purity of the water in the spent fuel pool is controlled by filter and demineralizers, and the temperature of the water is maintained by the use of coolers. In this example, we are going to show that the amount of material in spent fuel to be disposed can be surprisingly small. So the dimensions of a typical pressurized water reactor fuel assembly are 0.2 by 0.2 by 4 meter, giving a volume of 0.186 cubic meter. Assuming that on average 60 assemblies are discharged from a typical reactor, then the annual volume of spent fuel is 11.2 cubic meter, or almost 400 cubic feet. In US, there are currently less than 100 reactors, commercial reactors. So for 100 US reactors, this would be 39,400 cubic feet, which would fill a standard football field to a depth of less than 10 inches, assuming that the fuel assemblies could be packed closely. Therefore, from this example, we can conclude that the amount of the spent fuel to be disposed for the entire nation is not a very huge amount. This example will calculate the total amount of mass of fission product produced by the reactor. So the amount of fission products can be estimated by letting their mass be equal to the mass of fuel fissioned. For example, if we burned 1 kilogram of uranium-235, then that fuel is converted to almost the same amount of mass of fission product. So to produce 1 megawatt a day of thermal heat, thermal energy, it will burn 1.11 gram. For a reactor operating at 3,000 megawatt thermal, this implies 3.3 kilogram per day, or on an annual basis, the mass of fission product is equal to this coefficient 1.11 gram per megawatt a day, then times the power in megawatt, then times the duration of time in days. So times 3,000 megawatt thermal, then times 365 days per year. Then it will give us the result of 1,200 kilogram per year. So it means that this reactor is producing 1.2 metric tons of fission product per year. Then, if we assume that the fission product has a density of 10 gram per cubic centimeter, or 10 to 4 kilogram per cubic meter, then the annual volume is calculated in this way. So the volume is equal to the mass over the density. So the mass is 1,200 kilogram divided by 10,000 kilogram per cube meter, then we get only 0.12 cube meter per year. So this corresponds to a cube 50 centimeter per side. So if we are able to extract all the fission product from the spent fuel, then we can significantly reduce the volume of the high-level waste, which is one of the major advantages of reprocessing the used fuel, the spent fuel. The U.S. Department of Transportation and the NRC provide regulations on radioactive material transportation. A classification scheme for containers has been developed to span levels of radioactivity from exempt amount to that of spent nuclear fuel. For spent fuel, protection is required against 1. Direct radiation exposure of workers and the public, 2. Release of radioactive fluid, 3. Excessive heating of internal, and 4. Criticality. This figure shows the General Electric shipping cask. It consists of a steel tank of length 5 meters and a diameter 1.6 meters. When fully loaded with 7 PWR assemblies, the cask weighs up to 64,000 kilograms. The casks contain boron tubes to prevent the criticality. The boron can absorb the neutrons. The cask also contains heavy metal to shield against the gamma rays and water as needed to keep the fuel cool and to provide additional shielding. A portable air cooling system can also be attached when the cask is loaded on a railroad car. The cask is designed to withstand normal conditions related to temperature, wetting, vibration, and shocks. In addition, the cask is designed to meet performance specifications that stimulate real conditions in road accident. For example, the cask must withstand a 9-meter free fall, a 1-meter fall to strike a 15 centimeter diameter pin, a 30 minutes exposure to a fire at a temperature 800 Celsius, and a complete immersion in waters. Next, we will discuss the reprocessing. The physical and chemical treatment of spent nuclear fuel to separate the components, uranium, fission products, and plutonium is given the name reprocessing. This figure is a flow diagram of the separation of components of spent fuel. First, the spent fuel is unloaded and stored for further decay in a water pool. The assemblies are then fed into a mechanical shear that cuts them into pieces approximately 3 cm long to expose the fuel pellets. The pieces will then fall into baskets that are immersed in nitric acid to dissolve the uranium dioxide and leave the colloid house. The solution from this trap leach operation then proceeds to a solvent extraction process. After that, this chemical process will separate the fission products, uranium, and also the plutonium. The separated uranium has a uranium-235 content slightly higher than the natural uranium. It can either be set aside or re-enriched in an isotope separation process. The plutonium is converted into an oxide that is suitable for combining with uranium oxide to form a mixed oxide, MOX, that can compress part or all of the fuel of a reactor. Reprocessing has merit in several ways other than making uranium and plutonium available for recycling. First, The isolation of some of the long-lived transuranic materials would permit them to be irradiated with neutrons. From the neutron irradiation, we can turn those long-lived material into useful species, or innocuous forms for purpose of waste disposal. Means that we can turn the long-lived material to short-lived material or non-radioactive material by irradiating with neutrons. Second, numerous valuable fission products such as krypton-85, strontium-90, and cesium-137 have industrial applications or may be used as a source for food irradiation. Third, the removal of radionuclides with intermediate half-lives allow canister of waste to be placed closer together in the ground because the heat load will be lower. Four, several rare elements of economic and strategic national value can be reclaimed from fission products. Availability from reprocessing could avoid interruption of supply from aboard. 5. The volume of waste to be disposed would be lower because the uranium has been extracted. 6. Even if it were not recycled, the recovered uranium could be saved for future in breeder reactor blankets. Several countries like France, UK, Germany, Japan, and the former USSR have working reprocessing facilities and benefit from some of the preceding virtue. This example will calculate the mass of fission product produced from the annual electricity consumption of a typical US household. The average annual electricity use by a US household is about 11,000 kilowatt-hour, roughly 1,000 kilowatt-hour per month. For a burn-up of 33,000 megawatt-a-day per metric ton, the figure shows that the fission products account for 3.5% of the spent fuel mass. This figure can be found from the textbook. It just tells us the composition of the spent fuel, and 3.5% of the spent fuel mass is fission product. 33,000 megawatt-a-day per metric ton means that 1 metric ton of fresh fuel can produce 33,000 megawatt-a-day, this amount of thermal energy. Then, if 100% of the electric energy E were derived from nuclear power, each household would be responsible yearly for a fission product mass calculated from this formula. We will first convert the megawatt-hour to megawatt-a-day. Simply, we just divide the 24 hours. So here, we convert the megawatt-hour to megawatt-a-day. Recall that this is the electricity, and we need to convert the electricity to thermal heat. So we use the electric energy divide the efficiency, that is 1/3, so that we can convert the electricity to thermal energy. Then this amount of thermal energy is produced by how many tons of fuel is that we use this value to divide this coefficient. We use the total thermal energy to divide the 33,000 megawatt-a-day per tons. So we get the total amount of fuel that is used. Then we multiply this 3.5% because only 3.5% of those fuel is turned into fission product. This amount is very small. This value is very low in the unit of tons. Therefore, we then convert it to gram by multiplying a million, so that we can get the fission product mass in the unit of gram. So it means that each household electricity annual usage will produce roughly 1.5 gram of fission product. Next, we will briefly talk about the waste disposal method in US. We will start from the high-level waste disposal first. Decades ago, since 1987, Yucca Mountain in Nevada had been the proposed site for Yucca Mountain Nuclear Waste Repository. However, this project was abandoned in 2009, following years of controversy and legal wranglings. At this moment, there is no alternative plan proffered. At the present day, the spent fuel in US is stored on the site of the nuclear power plant, in the spent fuel pool or in the dry canister. There is no official permanent burial site yet. Starting in 1999, the military-generated nuclear waste is being buried at the Waste Isolation Pilot Plant in New Mexico. This figure shows the spent fuel at a geologic repository. You can see that the fuel assembly is encapsulated in this package and placed in this underground channel. For low-level waste, one popular technique is incinerations, in which the flue gases are filtered and the ash contains most of the radioactivity in a greatly reduced volume. Another method is compaction, with a large press to give a reduced volume and also to make the waste more stable against the further disturbance after disposal. The supercompactors that reduce the volume greatly are popular. A third approach is grading or shredding, then mixing the waste with a binder such as concrete or asphalt to form a stable solid. The method of disposal of low-level radioactive waste for many years was similar to a landfill practice. Waste were transported to the disposal site in various containers and were placed in trenches and covered with earth without much attention to long-term stability.